This is the final project presentation for Network Science Analytics course. Today I'm going to talk about data augmentation for graph neural networks, which uses graphons and graph-assisted distances. Data augmentation is extremely popular and useful in machine learning. The reason for that is that without collecting new samples, you can generate those and actually improve the model performance. The reason to use that is, for example, if you have small data set, you can generate new graphs and make the data set larger, or if it's sparse and has small variability between different samples, then you can make the model robust and more generalizable. However, it's harder for graphs because they are non-Euclidean structures. You cannot just downsample them or rotate like you can do for images. And also, once you generated those graphs, it's hard to measure whether it's a good fit for the model or not, or it might actually make it even worse. We'll go into test it on the binary graph classification problem when we have graphs and we are given only their topology and we classify them into two classes. For the node features, which are necessary for graph neural networks, we just took in and out degree for each node. To provide some context, I'm going to explain the key concepts from our algorithm. We're going to use graphons. Graphons are just matrices like here on the picture. The idea is that you slice the x and y axes into as many nodes as you want. And the point for between two nodes is the probability for these two nodes to have an edge. And also, we have sorted those graphons so that on the right, we have the highest degree nodes, and on the left, we have the lowest degree nodes. It's done so that for a few graphons, we can just take a linear combination of them, and it's actually the graphon for a group of graphs. We have also used Gromov-Wasserstein distances, and Gromov-Wasserstein distances give you a similarity measure between two graphs using some metric space. The idea is that two graphs might have a very different number of nodes and edges and different structure, but you can still measure how close they are. So we tested that for very similar graphs with Ardour-Rini with 1,000 nodes and probability 1%, and the distance was extremely small. But when we changed the probability from 1% to 5%, the distance rose. And we tested this with preferential attachment models, with small world models, and it also worked. For the data description, we have already a data set with 203,000 graphs, which have discussion, non-discussion based threads, and it's purely topology based. And so we used graphs of the size from just 11 nodes to up to 200 or 300 nodes. However, we only used a small data set of these graphs for the proof of concept because we would use a sparse data set and then later augment it so that actually data augmentation changes the result.
So let's talk a little bit about how we actually are going to do this data augmentation scheme. So first, what we want to do is we want to group the graphs together by the number of nodes and whatever label they have. Now, for each of these groups, what we can do is generate the SVM for all the graphs within that group and then average them together. And this gives us sort of an SVM that represents that group. Now, for each of these groups, once we have our SVMs, we can generate the graph that represents that group from that averaged SVM. We can then sample K graphs that are n times bigger than the original within those data set, within that group, and select a few of those that are closest to the SVM in terms of Gromov-Wasserstein distance. The reason why we decided to use distance to the SVM is since the SVM sort of represents the average of the group. This gives us a good idea of whether or not that graph belongs and makes sense to come from that group. We can then add those graphs to the data set and then rerun the neural network with the same architecture to see if it gives performance increases. Now let's talk about what we were actually able to do with augmentation. Here's an example. So on the left, we have one that was pulled from the data set, and on the right, we have one that we generated. As you can see, the topologies are fairly similar, which shows that this does have some promise in order to make bigger graphs. Let's talk about the actual neural network. So it has 3 hidden layers. Each of those layers is a graph convolutional layer. We did training over mean squared error, but testing was over. We used those results reported as accuracy. Learning rate remained consistent between runs to ensure that there was low variability between them. Here are the results that we actually got. So for the smaller data set of about 500 graphs, when we added 92 using our augmentation scheme, we only saw a performance increase of about 0.75. But then once we used double the amount and we added 200 augmented graphs or 200 generated graphs to the data set, we saw a performance increase of about 3%, which is much better and leads to more promise. But there were some problems we encountered. The performance improvements were dependent on the run. Only about 33% of the time, there was a marginal effect on accuracy, and the accuracy improvements we saw were typically between 0.5 and 3%. And as a note, the results on the previous page are averages from all those runs. And this kind of leads to the idea that concrete performance improvements, they're kind of hard to capture because the augmented data set does require bigger batches and more training time, and it sort of adds ambiguity to the results as whether we can concretely say, yes, this is works. There's also high variability within the data set in terms of graph size, and this could hinder our performance since it's such a small sample. And so a finer subset of those graphs could give us better performance since it sort of narrows down the problem and could give us a better idea of whether this is working concretely. Let's talk about what we're planning on doing in the future. So what we did now is just binary classification, but we want to expand that to multinomial classification, which generate different types of graphs, and seeing that leads to improvements. Then what we would want to do is introduce node features and see if we can do that, and then try to do that just for any arbitrary GNN. Finally, we'd like to say thank you. And this was a very fun class, very fun semester. And thank you, Professor Scara and Madeline, especially for all the assistance with the project. Our work is available on GitHub, so please take a chance to look at it.